Hello? Hello? Okay, good morning. We'll continue from where we stopped last time, and then we'll look at the factors affecting London forces. Just give me 1 minute. Okay, so factors affecting London forces. We have shape affects London forces. When you have long, skinny molecules that are packed together more efficiently, then you have stronger interactions. When you have short, fat ones that are packed, they're not well packed together, you have weaker interactions, just like you see here. And then also, when you have increase in molecular weight, London forces increase also with molecular weight. Then larger atoms, which have a lot of electrons around, also makes polarizing easier. So as you can see here, you have the smaller atom molecules here, and you have the higher the molecules, you have the higher the boiling point. So we can check now which of these have greater effect. Is it dipole-dipole interactions or dispersion forces? What's the answer? If two molecules are comparable, of comparable size and shape and dipole-dipole interactions, these to be likely will likely be the dominating force. So if two molecules are of comparable size and shape, dipole-dipole interaction will likely be the dominating force. But if one molecule is more larger than another, dispersion forces will likely determine the physical properties. So here you can see the summary of intermolecular forces. I'm not going to spend time on this because I'll give this note to you because we have to cover a lot. We still have a lot to go. So you can look at this. Then how molecular forces affect many physical properties. So the strength of the attractions between particles can greatly affect the properties of a substance. The strength. So let's see how this happens. For viscosity, molecular forces can affect viscosity. Resistance of a liquid to flow is called viscosity. It's related to the ease with which molecules can move past each other. So viscosity increases with stronger intermolecular forces and decreases with higher temperature. Another intermolecular forces also affect molecules in this other way, the surface tension. Surface tension results from net inward force experienced by molecules on the surface of liquid. So molecular forces also affect surface tension. Now let's look at kinetic theory of matter. Kinetic theory of matter states that matter is made of tiny particles which are in constant random motion. 2, matter possesses kinetic energy due to the motion of the particles. 3, the difference between the different states of matter is due to the nature and extent of motion and the separation between the particles. So looking at the solid state, look at solid, liquid, and gas. Solid have fixed shape and volume at a given temperature. Of course, that can change at different temperatures. Particles of solids are closely packed in an orderly manner. Solids have the greatest forces of attraction between their particles and when compared to energy possessed by the particles. Particles of solids undergo vibration about their mean position. Increasing the temperature of solids causes faster vibration of particles. That's why you see here that at fixed temperature, you have fixed shape and volume, but when you change the temperature, things change. So using kinetic model to explain the properties of solids tend to have the greatest density because the particles are usually closely packed. Solids have a fixed shape and volume because of the strong force of attraction between the particles. Particles hold to particles in their fixed positions. Solids are difficult to compress because of the lack of empty space between the particles. I think I have to make this slideshow for you to see more clearly. Yeah. Okay. So solids expand on heating due to increased energy of the particles at higher temperatures, like we mentioned before. This allows the particles to exist at greater distances from each other because the intermolecular forces are constant. Give me 1 second. So sorry about that. So like I was saying, that increasing the temperature of solids make their particles to move faster due to the gain in kinetic energy. So let's see how, using kinetic model, see how we can use kinetic model to explain the properties of liquids. Liquids have greater densities than gases because the particles are closely packed. They are closer due to the attractive forces. 2, liquids have fixed volume, but they take shape of their container because of the increased particle attraction. 3, liquids are not easily compressed because there's just so little space between the particles, so you cannot easily compress them. Liquids expand on heating due to the increased energy of the particles at higher temperatures. This allows the particles to exist at greater distances from each other because the intermolecular forces are constant. So you can see here the difference between solid and liquid. So you can see here the difference between solid and liquid here. In a solid here, you have the particles vibrating in a place, but not changing positions. You see the liquid here, particles moving and sliding past each other. So allow me to record this, sorry. Okay, so now, the gases also now, gases have no fixed shape or volume. And you know the reason. If they fill a container, the particles are so sparse, they're so sparse. Forces of attraction between the particles of gases are negligible. Particles in gases are so small that the actual volume of individual particles is negligible compared to the volume of the container. Particles are widely spaced and scattered and undergo random and rapid motion, and the average kinetic energy of the gas particles is directly proportional to the absolute temperature of the particles. The collision of the gas particles with the surface of the container causes gas pressure. So let's see how we can use kinetic model to explain the properties of gases. Gases have very low densities because the particles will space out in the container. They have no fixed volume and shape because of the negligible force of attraction. Gases are easily compressed because of the space between the particles. Order of ease of compression is gas is easier to compress than liquid, and liquid than solid. Gases express pressure, the exact pressure, because of the collision of the particles with the walls of the container. So explanation of change of state process like melting. When solids are heated, particles gain kinetic energy and vibrate more strongly. Attractive forces weakening in comparison to particle energy. Particles become free to move around. That is when melted, when heated. And in freezing, when liquids are cooled, particles lose kinetic energy. And attractive forces then strengthen in comparison to particle energy, causing particles to be restricted to a fixed position. And evaporating and boiling also, we're looking at change of state processes. So for evaporation occurs when the particles of a liquid escape to form vapor. On heating, surface particles gain more kinetic energy and they move faster. I don't think I want to talk much on this because I'll give you these lectures. You still have a long way to go. We have also condensation, which is the change in the physical state of matter from the gaseous form into the liquid form. So how do you determine melting point? Heat one end of the capillary tube in a Bunsen burner, fill about 1/4 of the capillary tube with substance and tie it to the thermometer. Insert the tube and the thermometer into an oil bath. Heat the constant stirring with constant stirring and record the temperature at which the first crystal melts, and then the temperature at which the last crystal melts. So you can see here phase change of matter changing from gas. You can interrelated from gas, solid, liquid. So you can see this. So let's look at another topic now. So I will share my slide for another topic. Okay. Hold on a little bit. So want to look at properties of gases. Properties of gases. Okay. Let's go on the slideshow. The properties of gases. Gases are one of those three common states of matter. They are composed of particles that are far apart in a constant random motion. And because of this, gases show unique properties that distinguish them from solids and liquids. I've mentioned some of these properties before. Let's just look at it. Compressibility. Gases can be compressed easily because there are large spaces between gas particles. An example is that of air in a syringe. It can be compressed by pushing the plunger inward. Another one is expansibility. Gases expand till they fill completely any container which they are placed in. And also, gases have low densities. They have very low densities compared to solids, liquids, and liquids because their particles are widely spaced. And also, we have diffusion, which is a gradual spreading of gas particles from a region of high concentration to a region of low concentration. You have example here, the smell of perfume spreading across a room. We also have the property of effusion. Effusion is the flow of gas particles through a tiny hole in a container without any significant intermolecular interaction. Example is air that slowly escapes from a punctured tire. That's effusion. Pressure. Gas pressure is caused by collisions of gas particles with the walls of a container. We will see this as we go on. And the factors affecting gas pressure are temperature, volume of the container, and the number of gas particles. So we also have gas laws and related properties. Planck's law states that at constant temperature, the volume of a fixed mass of gas is inversely proportional to its pressure. As you can see here in this mathematical expression, P1V1 is equal to P2P and P2V2. Then you also have Charles' law that at constant pressure, the volume of a fixed mass of gas is directly proportional to its absolute temperature. You can also see here the mathematical expression. You have Gay-Lussac's law, which says that at constant volume, the pressure of a fixed mass of gas is directly proportional to its absolute temperature. And the mathematical expression is also shown here. You have Graham's law of diffusion. The rate of diffusion of a gas is inversely proportional to the square root of its molar mass. So there's an example here I want you to look at. You will have it in the note. You go and practice it. A gas occupies a volume of 400 cubic centimeter at a pressure of 100 kilopascal. What will be its volume at 200 kilopascal? Solution is already here given to you, so you go and look at it. And another example from gas law is here. A gas has a volume of 250 cubic centimeter at 300 Kelvin. What will be its volume at 600 Kelvin at constant pressure? I've given you the solution here, so you go and look at it. We have this also under gas pressure. Another example, why does gas pressure increase when temperature increases? Why? answer is here. Increase in temperature increases the kinetic energy of gas particles, leading to more frequent and forceful collisions with the container wall. So that is why pressure increases with temperature. Now here, pressure and temperature relation here. I'm also showing you here on this slide, the pressure units can have Pascal, bar, atmosphere, torr, millimeters of mercury, pounds per square inch. These are the symbols and these are the values. So you can use it in calculations, depending on what problem is given to you to solve. And you can also see the temperature. In this case, you present it, you use Kelvin. So how you convert it is that the temperature that is given to you in degrees centigrade, you just add 273.15 and you have it in Kelvin and use it for your calculations. Now, equation of state. We have this equation of state. P is a function of N, B, T. I'm going to explain in the next slide. And you have empirical laws. Those laws I mentioned, Boyle's law and Charles' law, they are empirical laws. So these are the symbols for the pressure, the P, volume. You just look at that also. And also you see the chart here, the pressure volume dependence of a fixed amount of perfect gas at different temperatures. So each curve here is a hyperbola. That is, a PV is constant. PV is constant. So this is called isotherms, as you see here. Here, I give you some ideal the gas constant here. Gas constant here, which is R 8.31447. So you just look at these charts and see it. When you want to put it in different units, you can see them here. Okay. The explanation of the equation of state I just showed you, the equation of state P being a function of is equal to a function of NBT, is a thermodynamic equation that relates pressure P to the amount of substance M moles and volume, and the absolute temperature T for a system in equilibrium. So it defines the physical state of matter, allowing prediction of pressure if you know the volume, if you know the temperature, and you know that, then you'll be able to find the pressure. So the gas law, I've stated it before, the ideal gas law, or perfect gas law, the ideal gas or perfect gas, PV is nRT. So you go and look at this. I have to just try and go as fast as I can because of time. Okay. Partial pressure of mixture of gases. This one is linked to Dalton's law. Total pressure of gas mixture is equal to the sum of partial pressures of the gases. So you have here, partial pressure of the gas is proportional to the mole fraction X1. That's why you have this P1 is equal to X1 P. That is P1 or PI is that partial pressure. Xi is that mole fraction of that particular gas, and then P is the total pressure of the gas. So you can see it represented here pictorially, where you have the different partial pressures here. When you add them together, it gives you the total pressure of the gas. You also see here, let's see the compressibility factor. We mentioned that gas has that property, can be compressible, can be compressed. So we need to modify we need to modify ideal gas equation of state to accommodate non-ideality of real gas. Real gas is different from ideal. Ideal is like a perfect gas. So for ideal gas, Z, that is compressibility, is equal to 1. And deviation from 1 is a measure of non-ideality. So you can see this graph that the chart I've shown you here. The variation of the compression factor, which is Z, with pressure for several gases at 0 degrees centigrade here. So for a perfect gas that I mentioned, that's an ideal gas, the Z is equal to 1. That's compression factor is equal to 1 at all pressures, as you can see here. Then Van der Waals equation of state. So you see the equation here. When it is separated and written here, as you can see, the one that accounts for intermolecular attraction, and the other part of it accounts for volume of molecule. So A, B are constants depending on the gas. A and B are constant depending on the gas. And then here I also show you some Van der Waals coefficients for different gases. So to the next slide. The kinetic theory of gases assumes that the only contribution to the energy of gas is from kinetic energy of molecules. That means potential energy of interactions is negligible, as you can see here. The molecules have mass and diameter. The sizes of molecules is negligible. Molecules do not interact other than perfectly elastic collisions when separation of their centers is equal to D, the diameter. So you please go and look at this again. And then let's see the collision with the wall. Consider that you have a wall in the X and Y, Z and X, Y and Z plane. Molecules with a velocity in X direction will collide with the wall. So a molecule with volume Bx will collide with the wall in time delta t. So in this case, as you see here, I'm asking you, will this molecule collide with wall? This diagram I show you here, you see this particular one will not, and this other one will. Go and look at it again. So this is collision and momentum. Just give me, okay, all right. Molecular collisions. So you want to determine the collision frequency and the total number of collisions between gas molecules. So you assume molecules are hard spheres with diameters of d. You have two molecules will collide if they approach they approach the wall in distance d. A molecule moving through space at speed v will sweep out cylinder of volume v in delta t. Any molecule whose center is in this volume will be hit. So you see here the collision across the section, cross-sectional area of an imaginary sphere surrounding a molecule into which the center of another molecule cannot penetrate. So You can use this to check the collision frequency and the total number of collisions between gases. Okay, we have mean free path. What is mean free path? Lambda is the average distance between a molecule, the average distance that is traveled by a molecule between collisions. So you have here the relationship, how you can do this calculation in case you're given something like this in exam, or a question that relate to this. This is what you can use. And this is different for different gases, as I show you here, the collision cross sections for different gases. Okay, the other lecture, I'm trying to share the other one. I have them in bits and pieces. So just hold on for the next lecture. Okay. This lecture is on hybridization and shapes of simple molecules. We'll also look at valence forces, and we'll look at structure of solids. Hybridization is the concept of mixing atomic orbitals that are close in energy to form same number of new hybrid orbitals with equal energy and definite geometry. So these two newly formed orbitals are called hybrid orbitals. And the concept of hybridization was first proposed by Linus Pauling in 1931. It's just what you need to just have an idea of. So you can see these different orbitals as I show you here. We have the s orbital, we have the p. So p and with vector x, we have p x p y. We have p x p y p z, the different directions. So this is how the shapes look like, what you see here. So the hybridization of atomic orbitals, these are points you should note, that the hybridization of atomic orbitals take place either by reshuffling of all or some of the orbitals in the excited state. The hybrid orbitals have same shape, size, and energy. That means they are equivalent to each other. And the number of hybrid orbitals are equal to the number of reshuffled pure atomic orbitals. So the shape, size, orientation, and energy content of the hybrid orbitals are different from the pure atomic orbitals. The shape, size, orientation, and energy content of the hybrid orbitals are completely different from the pure atomic orbitals. The labels given to hybrid orbitals reflect the contributing atomic orbitals. For example, we have an sp hybrid orbital possesses equal amount of s orbital and p orbital character. So you can see here, these charts that I'm showing you here, for methane, the bonding in methane here, carbon is in sp3 hybridized state, where it has 4 sp3 hybridized orbitals. So you can see here the carbon at the ground state with the sp3 hybridized orbitals. Then you can see carbon at excited state here, and you can see here each 4 sp3 hybrid orbitals of carbon overlap with half-filled 1s orbital of 4 hydrogen atoms to form 4 bonds, 4 CH bonds. All the 4 CH bonds in methane are equivalent to, and then all of the CH bond angles are 109.5. You see the bond angle there. For ethane, both the carbon atoms are sp3 hybridized. So in this structure, you have the 3 of the sp3 hybrid orbitals of each carbon atom overlapping with 1s orbital of hydrogen to form the total of 6 carbon hydrogen CH bonds, while the remaining sp3 hybrid orbital of carbon overlap with the sp3 hybrid orbital of the adjacent carbon to form a CC sigma bond. As you can see here, you can see the CC sigma bond here, and then you can see the other 6 CH bonds. And the angle here is 109 degrees, thereabout. For ethylene, you have each bond atom is in sp2 hybridized state. And the structure, in this particular structure for ethylene, each carbon atom utilizes 2 of its 3 sp hybrid orbitals to form 2 CH bonds. This is by overlapping with the 1s orbital of hydrogen. The remaining remaining sp2 hybrid orbitals of each carbon then overlap with each other along the axis to form the CC carbon-carbon sigma bond. The unhybridized 2pz orbital perpendicular to the plane of sp2 hybrid orbitals overlap sidewise, as you can see here, with the other 2pz orbital on the adjacent carbon. So this is what you can see. You can see the excited state here, and you can see the hybridized state. For acetylene, 1 sp hybrid orbital on each carbon overlaps with 1s orbital of hydrogen to form a CH sigma bond, while the other sp hybrid orbital of carbon atom overlaps with the sp hybrid orbital of adjacent carbon atom along the axis to form a CC carbon-carbon sigma bond. Then the remaining 2 unhybridized 2p orbitals, that is the 2py and 2pz of each carbon, then overlap with each other sidewise to form 2 pi bonds. They overlap to form 2 pi bonds. So you can see here hybridization, the molecular geometry, and examples of the different hybridized states. For sp2 is tetrahedral, example is methane. For sp3, planar, trigonal, and the sp2 is linear. There are important points that I want you to note, that the hybridization of carbon, oxygen, or nitrogen atom can be determined by the number of pi bonds it forms. If it forms no pi bond, it is sp3 hybridized. If it forms 1 pi bond, it is sp2 hybridized. And if it forms 2 pi bonds, it is sp hybridized. So note this. So you can look at this. Again, this is just influence of hybridization of bond properties. You can look at this on your own. And then the bonding in methyl cation is here. So you see how this is. And then in methyl radical, And in methyl anion, those bondings are different. So you can see what happens in those different cases here. Then bonding in water. In this case, oxygen atom is sp3 hybridized. So you just go and look at this again, because I need to touch the other topics a bit before we finally leave. Valence forces. These are, looking at valence forces now, these are the attractive and repulsive forces between atoms. And these are what determine how they combine to form molecules and solids. So these forces arise primarily from interactions between positively charged nuclei, negatively charged electrons, electron-electron repulsion, nucleus-nucleus repulsion. So valence forces determine the following: bond formation, molecular geometry, bond energy, physical properties like melting point, hardness, and conductivity. It also determines chemical reactivity. So you can see how important the valence forces are. So we classify valence forces into two: the primary valence forces, which these are strong ones, and the secondary valence forces, these are weak forces. The primary ones involve electron transfer or sharing. I mean, this should inform you that this is talking about ionic and covalent bonds. And so we've talked of ionic bonds before. So this is one of the classified valence forces, ionic bond. And then the characteristics here of ionic bond are that they are non-directional, they have high melting and boiling point, they're hard and brittle, they conduct electricity in molten and aqueous states, usually soluble in polar solvent, that is compounds that are formed by ionic bonding. Now, the energy consideration here, ionic bond strength depends on charge magnitude, distance between ions, lattice energy, and Coulomb's law, which I've stated here for you. And we look at, remember also, we say strong forces, strong bond under the primary valence forces. So covalent bond is one of them. Example is that of methane. And then the different carbon shares 4 electron pairs with hydrogen there. We have different types here: the single bond, the double bond, and triple. So that's to do with the covalent bonding, strong force. And then the metallic is also one of those primary valence forces, or formed by primary valence forces. The metallic bonding occurs when positive metal ions are embedded in a sea of delocalized valence electrons. We've discussed this before in our first lecture, so we don't want us to spend too much time here. We have the secondary valence forces. That is the weak intermolecular forces, like the van der Waals forces. We have talked about this. The van der Waals forces, which include the dipole-dipole interaction, and also the London forces. And so we have also this other weak intermolecular force. We have the hydrogen bonding, which we have discussed before. So interatomic potential and bond formation, when we have two atoms approaching each other, attractive forces dominate at long distances, and repulsive forces dominate at short distances between those two atoms. Equilibrium bond distance occurs at minimum potential energy. So, sorry, let's slow down. We have valence bond theory, which was developed to explain covalent bonding. And the principles are that bond forms when atomic orbitals overlap. Overlap leads to shared electron density, and also greater overlap leads to stronger bonds. Here we have still here, you can apply the valence bond theory to hybridization. Now, there are several factors that affect valence forces. We have atomic size, we have electronegativity difference, we have electron configuration, we have also polarizability. Then we have bond order. So here you can compare the primary valence forces here. I've shown it to you, the different ways you can compare them. And then the importance of the valence forces are, the valence forces determine structure of solids, chemical reactions, biological molecule stability, mechanical properties of materials, electrical behavior of materials. For example, diamond is extremely hard due to strong covalent network bonding. Gold is malleable due to metallic bonding. We just have the very last, maybe you can just bear with me. So you just complete this. It's not much. Structure of solids. Solid is one of the three main states of matter along with liquid and gas. Molecular motion for the particles in a solid is confined to a very small vibration, very small vibrations of the atoms around their fixed position. The vibration is just very, very minimal. So solids have a fixed shape that is difficult to change. Solids also have definite volume. That means they keep their size no matter how you try to change them. So large majority of substances that we have are solids. And the distinctive features of solids are here. They have definite shape, they are rigid and hard, and they have fixed volume. So if you look at these three diagrams I show you of solid and liquid and gas, you can see how the particles are dispersed or scattered or quite close, tight, like in case of solid. There are two types of solid, and these two types of solids have different characteristics. We have the amorphous solid, and we have the crystalline solid. For the crystalline solid, the main characteristics of crystalline substances are that they are orderly arranged. They have orderly arrangement. Then the crystals are always bound by plane faces. The faces of crystals always meet at some fixed angles. Crystalline solids exhibit an anisotropy in many of their properties. So you can see here what I'm showing you here in this diagram. That's how it looks like. And then transition from solid to liquid. That's another property, that is melting point. Can melt. Crystal solid, they have very sharp and distinct melting point. Then crystalline, also another property is that they exhibit definite heats of fusion. We have different types of crystalline solids. We have the ionic solid, which you can look at again. We have molecular solids, and we have network covalent solid. In this one, there are no individual molecules. The atoms are covalently bonded in a continuous network, resulting in huge crystals. That is this third one. And then, now we have amorphous. Let me just talk a bit about amorphous solid. Here, the particles do not have a repeating lattice pattern like crystalline solids. These ones are also called pseudo-solids. The examples of amorphous solids include glass, rubber, gels, and most plastics. These are amorphous solids. An amorphous solid does not have a definite melting point. Instead, it melts gradually over a range of temperatures. The reason is because the bonds do not break all at once. That means an amorphous solid will melt into a soft, malleable state before running completely into liquid. Amorphous solids also, they have no characteristic symmetry like crystalline. So they do not have regular planes of cleavage when you cut them, and the edges may be curved. They are called isotropic because properties such as refractive index, conductivity, and tensile strength are equal regardless of the direction in which a force is applied. So these ones are called isotropic, whereas the crystalline are anisotropic. Okay, I think this is the end of the lecture. Thank you for bearing with me. And I will send all information to you. I'll send the recorded note. I will send the YouTube link. You already have that. And I will send even my lecture note, the slides also to you. So this is the end of our lecture. And